Good morning, students. I am Dr. Radhakrishnan Srinivasan, Associate Professor in Freshman Engineering Chemistry Department. So today we will see electrochemistry, the first module in your engineering chemistry syllabus. What is electrochemistry? Why it is important? So electrochemistry is very important for engineers. Why? Because it has direct applications in the form of batteries, your laptop batteries or lithium-ion batteries. And you know that batteries nowadays are in all electronic gadgets. Without lithium-ion battery, there's no technology today. So all electronic devices are supported by lithium-ion batteries, your cell phone, your Android cell phones, laptops, and many electronic gadgets. Okay, so what is electrochemistry? Electrochemistry is a branch of chemistry which deals with the transformation of electrical energy into chemical energy or chemical into electrical energy. Okay, so when you say electrochemistry, obviously the electrons are involved. So there are different types of materials which some materials may conduct electricity due to the passage of electrons, some may not, and some are intermediate. So first we will see the different categorization of substance based on their conductivity or capability of capability of conducting electrons. Electrical conduction. The substances are divided in different types depending on the capability of flow of electrons. Conductors, for example, first type is the conductors. So this is the first type. So the substances which allow electricity to pass through them are called conductors. So there are several examples, normally metals, metal sulfides, acids, alkalis, fused salts, salt solution. Fused salts means NaCl fused salt. Okay, NaCl in the form of fused salt will conduct electricity. Okay, so we have seen conductor and its example. Similarly, we have other types of substances which doesn't conduct electricity. We call them as non-conductors or sometimes insulators. Okay. Insulators, and there are also semiconductors which partially conduct electricity, and their conductivity values is in between a conductor and an insulator. So in conductor we have two types, metallic or electronic conductors and electrolytic conductors. Okay, so we will see more into this electrochemistry in the following slides. One more point in semiconductors. Semiconductors actually having the conducting property in between a conductor and a non-conductor or insulator. And their conducting properties can be modified, that means increased by the addition of certain impurities called doping. So when you say doping, we intentionally add impurities to improve the electrical properties of conducting properties of semiconductor. So if you, in silicon is a semiconductor example, if you add phosphorus or arsenic or having the valency 5-valent, okay, and silicon, it's a 4-valent. So when you add a small amount, doping means a small amount is enough. Okay, like less than 1% is enough. Okay, so it produces N-type because there is one electron in excess in these impurities than silicon. Okay, so similarly, if you add third group elements like boron, aluminium, silicon will produce P-type semiconductor. P-type semiconductor means it is having holes, okay, having plus charge, whereas N-type is having negative electrons excess. Okay, so opposite of electron is holes, which is having a positive charge. So they form P-type semiconductor. Okay, Okay, next. What is an electrochemical cell? Electrochemical cell is also called galvanic cell. So galvanic cell is a device in which chemical energy is converted into electrical energy. Okay. Daniel cell is an example of galvanic cell. So here in this figure we can see zinc dipped in zinc sulfate electrolyte, copper dipped in aqueous copper sulfate solution. So this is anode, negative charge, and this side is cathode, okay, positive charge. Zinc acts as an anode, copper acts as a cathode, where the two electrodes are electrically connected, okay, and they have separated by a porous disc. We call this as a salt bridge in the next slide. So what happens here? Electrons will move from anode to cathode in an electrochemical cell. How electron is produced here? Because zinc dissolutes into ions Zn2 plus. Okay, this Zn2 plus zinc gives Zn2 plus 2 electrons. Okay, this is the reaction happens here. These 2 electrons actually move to the cathode through this external circuit, and here the copper 2 plus ions in the aqueous solution accepts this 2 electron and get reduced to copper and deposited over this copper rod. Okay, so what is happening here? This side is a reduction reaction in the cathode, and in anode it is a oxidation reaction. Okay, so oxidation reaction liberates electron, and that electron accepts in the by the copper in the reduction reaction. So this is constitutes a galvanic cell, and this is called zinc copper couple, or zinc copper electrochemical cell. In short, they can also say couple. Okay, so we will further see this explanation of this Daniel cell copper zinc in the next slides. Okay, so as we have seen this Daniel cell just now, that we have 2 electrodes. One is zinc sulfate, and we have zinc electrode, copper rod in copper sulfate. These 2, I told, it is connected by a salt bridge. This is called salt bridge, and these 2 are electrically connected. Okay, okay, so actually this Daniel cell is made up of 2 half cells. One is oxidation and another one is reduction. Zinc is anode oxidation and copper side is a cathode reduction. We have seen this before, and the reactions also I have written. In anode, this is oxidation reaction. Zinc gives Zn2 plus 2 electrons. At cathode, it's a reduction. Copper 2 plus 2 electrons gives copper. This is reduction reaction. So the movement of electrons from zinc to copper produces a current in the circuit. The overall, this is called overall cell reaction. Okay, overall cell reaction. Okay, so we get cancels out. This 2 electron and this 2 electron cancels out, and remaining we write it as overall cell reaction. So here this is called, zinc is a anodic half cell, copper is a cathodic half cell. Okay, so there are 2. The cell is made up of 2 half cells. One is oxidation or anodic half cell. The other is a reduction or cathodic half cell. Okay, both the half cells are connected by a metallic conductor, internally connected also through salt bridge. Salt bridge is nothing but a U-tube, it containing concentrated solution of KCl or ammonium nitrate in agar gel, and it is contained in a porous pot. It provides electrical. Actually, the role of salt bridge is it doesn't allow the 2 electrolytes to mix with each other, and also only the ions transport between the two electrodes that we have shown that in the previous slide. The two only ions will flow from one bath to another bath and not the overall electrolyte. Okay, so thereby it maintains the electrical neutrality. Okay, next. So again we are showing this zinc copper Daniell cell in the same way here. Here you can see clearly that this is zinc strip and this is zinc sulfate solution. This is copper sulfate solution, copper strip, and this is a salt bridge where it is made up of KCl, and this is these are porous plugs. Okay, and yeah, the connection is given here from anode to cathode. The electron move like this from anode to cathode. This is anode zinc, cathode copper. The reactions, oxidation, reduction, everything is shown here again. Okay, so this is zinc plus 2 and copper 2 plus concentration is 1 molar. Okay, and this cell develops 1.1 volts at 25 degree centigrade. Okay, 1 volts at 1.1 volts at 25 degree centigrade. So this clearly explains whatever we have seen so far in this Daniell cell, zinc copper Daniell cell. Okay. Next, representation of galvanic cell. That means this type of electrochemical cell or galvanic cell, there is a notations used for its representation. Typically, it is represent zinc copper galvanic cell is represented like this. Okay, zinc 1 dash zinc 2 plus bracket concentration 2 dashes copper 2 plus bracket concentration 1 dash copper. So normally what is the notation in writing the cell representation? This is cell representation. Okay, electrochemical cell representation or galvanic cell representation. Anode is written on the left. Okay, here zinc anode. Okay, zinc anode. Cathode is written on the right side. This is cathode, copper cathode. You know that anode undergoes oxidation, cathode undergoes a reduction in an electrochemical cell. Okay, this is concentration of the aqueous solution of zinc sulfate or copper sulfate. Okay? So this is the way we represent the electrochemical cell. So any cell given in this form, we can know which is cathode, which is anode. From the representation, we can find out which is undergoing oxidation, which electrode is undergoing reduction, like that. Okay. Next, EMF or electromotive force. EMF or electromotive force. In short form, EMF. The difference of potential which causes flow of electrons from an electrode of higher potential to an electrode of lower potential is called EMF of a cell. Okay. So when you use two electrode, one electrode is having a higher potential and another electrode is having a lower potential. So due to this potential difference is developed in the cell. That is what we call as EMF or electromotive force of an electrochemical cell. This is calculated by EMF of a galvanic cell is calculated by a reduction of cell potentials using the following expression. Okay, E cell is equal to E of right minus of E of left. So we can also say E cell is equal to, right side is reduction potential of copper minus of reduction potential of zinc, which is left side oxidation. This is for zinc copper galvanic cell. Now I know the reduction potential of copper, which is plus 34 volts, minus of, and the reduction potential of zinc is 0.76. So we get EMF. E cell means EMF of the cell. This is the representation. E cell meaning EMF of cell, EMF of the cell, okay, which is nothing but 1.1 volts. This is what we have seen in the previous slide, that this cell gives minus 0.76, okay. So which gives 1.1 volt for zinc copper electrochemical cell. Okay. Next. So we have explained the same thing again. EMF is calculated by E cell is equal to E of right. E means, here what we mean by E. E cell means EMF of the cell. E right means reduction potential of right hand side electrode, which is in zinc copper example. Okay, right hand side is copper, which is reduction. And E left means reduction of left side electrode, which is zinc, undergoes oxidation. Okay. Okay. Which is used to measure EMF of the cell. Normally in the lab we use potentiometer. Potentiometer actually, if you construct a cell, anode, cathode, electrolyte, okay, and then it is connected to a potentiometer, it will give what is the potential difference, okay, as in the form of E cell, okay, EMF cell, okay. So, okay, some applications of EMF measurements, potentiometric titrations can be carried out, okay. You can carry out to know the oxidation amount of iron in the iron content in the Fe3 plus ions, okay. Transport number of ions can be calculated. Transport number of ions means how speed the ions are moving. It is a little higher part of electrochemistry will come. pH can be measured. pH, it can be in all labs. pH. What is a pH value? pH is a very, very important in chemistry, so that can be measured using the EMF measurement. So these are all the applications. Okay, next. Another example of a voltaic cell at ions 0.1 molar. The concentration of ions are at 0.1 molar. For example, cadmium, this is called, you can say cadmium-silver cell or cadmium-silver. You can also say cadmium-silver couple, or you can say cadmium-silver system. You can say different by name, which is cadmium Ag electrochemical cell or voltaic cell. Concentration of ions is 0.1 molar, for example. So what is anode here? This is the cell representation. Okay. From this cell representations, we know cadmium is undergoing oxidation. Ag is undergoing reduction. This is anode. Cadmium is the anode. Reaction is this. And cadmium is the anode electrode. So cadmium undergoes, cadmium gives reaction cadmium 2 plus 2 electrons. And cathode is a silver electrode, which gives 2 Ag plus 2 electron gives 2 Ag. This is the reduction reaction. So anodic oxidation. So always in electrochemical cell, anodic oxidation and cathodic reduction. In electrochemical cell, it is always anodic oxidation and cathodic reduction. So here, cadmium is the anode. The reaction is here. Cathode is Ag. Reaction is here. Okay. And the construction again, as we have seen for zinc copper. So this is cadmium anode, Ag cathode, and both the electrodes are connected by a salt bridge. We know it contains KCl inside, okay, plus some agar gel, and there are some porous plugs in this, and these two electrodes are electrically connected. Okay. Next, this cell develops 1.2 volts. We have seen zinc copper cell 1.1 volts. Here it is 1.2 volts. It's another example. Okay. Now we have seen studied some Uh, we have studied some important points in electrochemical cell. There is another type of cell which we need to just introduce, nothing more. We are not going to concentrate more on this type of cell. We are studying more on this galvanic or electrochemical cell, but still we should know the difference between these two basic types of electrochemical cell. One is galvanic cell and another one is electrolytic cell. So what is the basic difference between these two? Galvanic cell or electrochemical cell converts chemical energy to electrical energy, whereas electrolytic cell converts electrical energy to chemical energy. Okay, so in electrochemical cell, anode is negative, cathode is positive, whereas in electrolytic cell, anode is positive, cathode is negative, reverse. Salt bridge is required. We have seen in the previous two examples, salt bridge is needed, whereas salt bridge is not required for electrolytic cell. And the galvanic cell or electrochemical cell is reversible and spontaneous. Okay, reversible means we put the arrow mark in the reaction like this. Okay, means X plus Y gives A plus B. If you put arrow mark like this, means it is forward reaction and backward reaction are possible. In equilibrium, they have the same rate. They are in equilibrium. Okay. EMF of the cell is positive for a electrochemical cell, and process is irreversible and non-spontaneous in electrolytic cell, and EMF of the cell is negative in electrolytic cell. So what is meant by spontaneous? So we will see spontaneous condition for a reaction to be spontaneous is given by change in free energy of the reaction. Delta G is equal to minus NF E. E, you know, it's a EMF. So if delta G is equal to negative, then a reaction is spontaneous, or you can say feasible. Okay, feasible or possible that reaction will occur. So what is meant by if EMF of the cell is positive, then delta G is negative. So it becomes spontaneous. Okay. Okay. Next we see electrode potentials. E, capital, represented by capital E. So what is meant by electrode potential? What is meant by single electrode potential? What is meant by standard electrode potential? So we have seen the construction of, we have seen the how the galvanic cells have been represented, how diagrammatically it is connected and all we have seen, and what is their voltages we have seen. So now we move to electrode potentials. Okay, single electrode potential and such standard electrode potential. It is represented by capital E, and this is represented by E naught. So wherever we put this superscript 0, that means it is standard conditions. Under the standard conditions we are talking, that means E0 will put. Okay. So when a metal rod is dipped in its own solution, we have seen copper rod dipped in copper sulfate, zinc rod dipped in zinc sulfate, cadmium rod dipped in cadmium sulfate. Like that. When a metal rod is dipped in its own salt solution, the metal ions tend to have, or you can say have the capacity to lose electrons or accept or gain electrons. Okay. If it loses electrons, it is oxidation. If it gains electrons, it is reduction. So the process of oxidation or reduction, it depends entirely on the nature of metal. Okay. For example, we have seen zinc undergoes oxidation, copper undergoes reduction, we have seen, and also we have seen cadmium oxidation, Ag reduction. So it depends on the nature of metal, whether it accepts the electron and undergo reduction, or it releases electrons, lose electrons and becomes anode or undergoing oxidation reactions. Okay. So in this process, there develops a potential difference between the metal atom and its corresponding ion, which is called the electrode potential. So the development of potential difference between the metal atom and its ions is called the electrode potential. There is a dynamic equilibrium between the metal and the metal ion, and the potential difference between the two is called electrode potential. Electrode potential is measured in volts. Okay, what is standard electrode potential E naught? The potential exhibited by single at unit concentration of its metal ion at 25 degrees centigrade, unit concentration 25 degrees centigrade, is called standard electrode potential E naught. So for example, single electrode potential of copper 2 copper becomes standard potential when copper 2 plus is 1 molar. Okay, that is unit concentration. Okay, and E naught value of single electrode is determined experimentally by combining with a single electrode with standard hydrogen electrode. Okay, this is important point. And we cannot measure the potential of single electrode. We cannot measure the potential of single electrode because we can only measure the EMF of a cell, not the single electrode. So how it will become a cell? We have to connect it with a reference electrode, which is standard hydrogen electrode. Standard hydrogen electrode whose potential we will keep it as 0 volts. Okay. So when we combine with this standard hydrogen electrode, for example, with a copper, here we take example copper. When we connect this copper with the standard hydrogen electrode, it forms a cell. So since E naught value of standard hydrogen electrode is 0, whatever we get as EMF, it is the value. Whatever we get as EMF, it is the E naught value of copper. Okay. So that is how electrode potentials of different metal and its ions are calculated by combining this electrode with a standard hydrogen electrode as a reference to measure EMF. Okay, single electrode potential we cannot measure directly what is its EMF. So we need two electrodes and their electromotive force, that is EMF, can be measured by connecting it with a standard hydrogen electrode. And there is one more standard hydrogen electrode called saturated calomel electrode. We will see these things little bit in the later slides. Okay, moving to next slide. Okay, see this metal and its ions, different metal ions. If you connect with hydrogen, standard hydrogen electrode and measure their potentials, okay, so you get different values like this. For lithium, lithium plus this is, for copper 2 plus copper is this, like that. For different metal and its metal ions, we get different E naught in volts. Okay. So their reactions are represented here, half cell reactions. So what is electrochemical series, or we can also say EMF series? The electrode potentials of different electrodes can be determined by using standard hydrogen electrode that I have told in the last slide. The potential of hydrogen electrode is assumed as 0 volts. This also I told you. So the measured EMF itself is the standard electrode potential of that electrode. Okay. Since hydrogen electrode has 0, whatever the measure has come from the electrode itself. Okay. The arrangement of different electrode potentials from highest negative to highest positive are called electrochemical series or EMF series. See, it is we are showing it from negative highest to highest positive. So this type of tabulation, all these measurements are done according to with respect to hydrogen. as a reference, which is in the center. Okay. So above are all oxidation, below are all reduction, above all are under anode, below are all cathode. But however, whether it loses or accepts electrons, we represent all these things in the reduction, which is a notation. It's a common notation in electrochemistry that the cell potentials are represented in the form of reduction potential. Either it has positive or negative poles. We write always in lithium plus bar lithium, K plus bar K, like that. It is a standard notation that we represent in the reduction potential only. Okay. So even though zinc, we know very well that it undergoes oxidation and its volt is minus 0.76 volt E value, okay, which is given here. Okay. In copper, we have seen example, very well known example, zinc copper electrochemical cell, which gives copper. Okay. So which is again here. Actually, it is given wrong. It should be plus 0.34 volts. Okay. E naught is equal to plus 0.34 volts. So that we know that EMF is equal to 1.1 volts. E of reduction minus of E of oxidation. Okay. Okay. So this, from this we can know many electrochemical cell, whether it acts as a, if any cell representation is given based on the values, we can say whether it undergoes oxidation or reduction. Higher the value, okay, more negative the E naught value, more negative the E naught value, it will undergo easily oxidation. More positive, it will undergo easily reduction. Okay. So when you have zinc copper couple, zinc is having in minus 0.76, copper is having in plus. So copper undergoes reduction because of its electrode potential. Zinc undergoes oxidation because of its electrode potential. So more negative will undergo oxidation, less negative or positive will undergo reduction out of the given two electrodes. Okay. So by this way, you know that any two electrodes, zinc copper is well known. So any two other metal can be given. From its E naught values, we can find out which one will undergo oxidation in the reaction, which one will undergo reduction in the reaction. Okay. Next. So this is again, there is a same electrochemical series table, standard reduction potential at 25 degrees centigrade, E naught values, okay, is given for more number of reactions. Okay. So it starts with here, positive. Fluorine gas plus 2 electron gives 2 fluoride aqueous. E naught value is 2.87. From that to maximum negative, it's lithium. Lithium aqueous plus electron gives lithium solid. So we comes from more positive and then slowly decreases to 0 for a hydrogen electrode. This is standard hydrogen electrode, which is used as a reference to measure the E naught values of all these reactions. Okay. And then it decreases and maximum negative for lithium. So what this table tells is more positive. I have told in the last slide, again I am emphasizing the same. More positive means stronger oxidizing agent. That means more readily accepts electron. That is reduction in the reaction. More negative means stronger reducing agent or more readily gives the electrons, means oxidation. Okay. So when you come from positive to more negative, this more negative side is a stronger reducing agent. So when you go from below more negative to high positive, we call it a stronger. High positive side is stronger oxidizing agent. Lower negative side is stronger reducing agent. So what is a reducing agent? Reducing agent, how do you define a reducing agent? Reducing agent is nothing but which reduces the other species by oxidizing itself. Whereas what is oxidizing agent? Which oxidize the other ions or species by reducing itself. Okay, so this is the significance of EMF. So this is the significance of EMF series or electrochemical series. Next, Nernst equation, which is very, very important in electrochemistry. Nernst equation. Okay, how will you get the Nernst equation? So now, Nernst equation, what does it tell? It tells us the effect of electrolyte concentration on electrode potential. That is the concentration of Mn plus ions relation with electro potential. Okay. Generally, let us consider a reduction reaction. Mn plus an electron, which should be in reversible form, gives M solid. Okay. So for this electrode reaction, free energy can be calculated provided if you know G naught, delta G naught, gas constant, temperature, activity or concentration of product and reactant. So G is equal to G naught plus RT ln, which is called normally Q is equal to activity of product. Basically, this is RT ln Q. Q is equal to activity of product by activity of reactant. So we already know that delta G naught is equal to minus NF E naught. Okay. Change in free energy at standard change in Gibbs free energy is equal to minus NF into standard electrode potential. So we know that delta G is equal to minus NFE, delta G naught is equal to minus NF E naught. Okay. So this is basically we are showing how we will arrive at the Nernst equation, derivation. So E is equal to, we have seen if you divide this expression, if you substitute this expression, it will become minus NFE is equal to minus NF E naught plus RT ln A product by activity of reactant. Okay. So, since we know delta G is equal to NF minus NFE and delta G naught is equal to, we have written like this. Now, we have written this equation. Now, if you divide this by minus NF, what will you get? We will get E is equal to, you get this, right? E is equal to E naught minus RT by NF ln activity of product by activity of reactant. Okay. So this is how we proceed to the next, which is nothing but it is written here. Okay, this is in log. If you multiply by 2.303, it will become into a natural logarithm to the logarithmic to the base 10 log form, ln form to log form. If you multiply by multiplying by 2.303 factor. Okay. Okay, so this is the form of Nernst equation. Okay. So capital E is electrode potential, E naught is the standard electrode potential, F is Faraday of electricity, which is nothing but 96,500 Coulomb. Capital T is the temperature at 298 Kelvin, standard temperature. Gas constant is the R is capital R is gas constant, 8.314 in kilojoules. This is not kilojoules or joules. Okay, this is not kilojoules, this is joules per mole per Kelvin. 8.314 joules per mole per Kelvin, which is wrong unit here. Okay, so A is activity, is nothing but concentration related at 298 Kelvin. Okay, so putting these values of F and R in this expression, we get E is equal to E naught minus 0.0599 N by N. Other than N, everything else is a constant. So if you if you substitute those constants, we get this expression. Now in dilute solutions, activities may be replaced by molar concentration terms, molarity. So this expression becomes E is equal to E naught minus 0.0591 by N log concentration of metal solid by metal N plus aqueous. Normally, concentration of metal is equal to 1. It is considered as an activity, unit activity. Okay, that is activity of 1 solids. So for pure solid, metal concentration of metal is equal to 1. So this expression becomes E is equal to E naught by N log concentration of 1 by concentration of M. This is called Nernst equation, okay, which is very important. So Nernst studied the theoretical relationship between electrode reaction and corresponding cell EMF. This relationship of E is equal to E naught minus 0.0591 by N logarithmic to the 1 by concentration of Mn plus is called Nernst equation. Okay, this expression is called Nernst equation. Okay, next. So we know that this is, here it should be 1 by, it is not concentration of, okay, it should be log of 1 by concentration of Mn plus. This is Nernst equation. So now consider a galvanic cell. Okay, so you consider A times capital A plus B times capital B. AB is the number of moles of the reactants, gives C times capital C plus D times capital D. So A, B, C, D are number of moles respectively at equilibrium. Okay, so here for this, how will you write the Nernst equation? E is equal to E naught minus 2.303 RT by NF log concentration of C power C into concentration of D power D by, this is nothing but what you called as Q. Okay, Q is equal to, we have written before, activity of product by activity of reactant, which we are writing it in this form. Okay, this Nernst equation is applicable for determination of EMF of cell. Okay, which we normally written like this, E cell or electromotive force. So similarly for a cell reaction, for example zinc, okay, plus copper 2 plus, this is the zinc copper electrochemical overall cell reaction, gives zinc 2 plus plus copper. So for this we will write the Nernst equation like E is equal to E naught minus 2.303 RT by NF log concentration of zinc 2 plus 1 molar by copper 2 plus 1 molar. See, this 2.303 RT by F can be substituted. This is constant, this is constant, this is constant, which gives 0.059 by N. Okay, this is what which is we are representing here. Okay, the N is varying from reaction to reaction. N can vary, but these are all constant. Other things are constants. Okay, see, this is the diagram for standard hydrogen electrode, SHE. Standard hydrogen electrode. Okay, so we have already seen that standard hydrogen electrode is taken as a reference to measure the electrode potentials of different systems. We have seen the EMF series or electrochemical series. So here we have platinum electrode for connectivity, which is here, and then E naught value is considered as 0 volts for standard hydrogen electrode at 25 degree centigrade. concentration of HCl, here H plus ion is 1 molar. Atmospheric hydrogen is 1 atmospheric hydrogen we have to flow through. This is the hydrogen we have to flow through the system. Okay. So this is the platinum plate which acts as a electrical connectivity to the cell. Okay. And hydrogen outlet is this. This is a salt bridge if you want to connect any other system here. Okay. Any other system here, for example, zinc or copper or any other system. We can connect and find the electrode potential of this EMF of the cell, which is nothing but electrode potential of this electrode under study, which we have seen before also. Okay. But what is the practical difficulty in this is practically impossible to maintain the pressure of hydrogen at 1 atmosphere. The standard conditions is very difficult to maintain because 1 atmospheric pressure hydrogen is very difficult to maintain throughout the experiment. So normally secondary electrodes like saturated calomel electrode. Calomel is nothing but Hg2Cl2. It's called calomel. Okay. So for all practical purposes and in labs, standard hydrogen electrode is no more used. It's only people are using secondary electrodes like saturated calomel electrodes. Spelling mistake is there. It is in short form saturated calomel electrode, SCE. Okay. Saturated calomel electrode, SCE, instead of SHE, standard hydrogen electrode. So this is saturated calomel electrode is more preferred because reference electrode for all the practical purposes, because as I told, there is difficulty in maintaining the hydrogen gas of 1 atmosphere in hydrogen electrode. So in labs and in many practical purposes for measuring the EMF, saturated calomel electrode is used as a reference electrode instead of hydrogen electrode. Okay. What is saturated calomel electrode? Calomel electrode is a glass tube having 2 side tubes. Pure mercury is placed at the bottom of the vessel and is covered with a paste of Hg and Hg2Cl2, mercury and mercuric chloride, Hg2Cl2, which is called calomel. Okay, there should not be any gap here. Okay, it should be read as Hg2Cl2. And KCl solution of known concentration is filled through the side tube. Okay, so platinum wire, as we have seen in the hydrogen electrode, platinum wire is sealed into the glass tube, which is in contact with mercury. The KCl solution is filled in the left-hand side tube, which helps to make the connection through a salt bridge with other electrode, which potential has to be determined. So, one side saturated calomel electrode and another side is connected to your metal system, which you want to measure the electrode potential. Okay, through a salt bridge. So this is the salt bridge. Okay. So when the cell is set up, is immersed in the given solution of metal, the concentration, the electrode potentials of calomel electrode at different concentration. Again, it's a reference electrode. So reference electrode means whose electrode potential is known. Okay, at the particular concentrations. So you use this known reference electrode to find the unknown metal electrode potentials on the other side. It is connected like this, SCE one side, metal to be studied another side. This two system is connected by a salt bridge. Okay. For example, the electrode potentials of calomel electrode of different concentration at 25 degrees centigrade are 0.1 molar KCl, mercury chloride, mercury, platinum. It is 0.33 volts. For 1 molar, next, this should be in the next. For 1 molar KCl, it is 0.28 volts, which is called saturated calomel electrode, SCE, which is normally used as a reference electrode. Or another concentration it has 0.24 volts. The corresponding electrode reaction is HgCl2. Okay, Hg2 2 plus. Okay, plus 2 electron gives 2 Hg plus 2 Cl minus. This is the electrode reaction of saturated calomel electrode reference, used as reference electrode. Okay. So this is the electrode used as a reference electrode called saturated calomel electrode. Okay. Next, what are the merits, advantage? The concentration of chloride remains constant. Potential of electrode remains constant with temperature. Easy of oxidation reduction reactions. Its construction is simple and easy to maintain. It's inexpensive. And pH can also be measured by combining hydrogen or quinhydrone or glass electrodes along with saturated calomel electrode. So these are all the merits or advantages of saturated calomel electrode. Demerits. What is the demerit? Solubility of KCl is sensitive. KCl can be replaced from time to time, has to be replaced from time to time. Mercury is toxic. We all know mercury is a toxic heavy metal and it possesses health hazard. So in many places wherever environmentally toxic substances are there, it has to be replaced with a greener, that is less toxic things. So mercury in this case is toxic. It possesses health hazard if it spills, if it falls down, if the electrode gets broken and mercury comes in contact with the skin, it will affects the it will create damage to your skin, and also it can enters into your body through the skin and it will give lot of ill effects. Okay. So with this slide, we will finish this hour with this class. So we have seen in a short form, work done in a redox reaction is given by thing. This is a maximum non-expansive work according to thermodynamics. Okay. So non-expansion work is a electrical work. Okay. So expansion work we have seen in in thermodynamics, like contraction, expansion, contraction. Whereas non-expansive work is electrical work, which is coming here, okay, in electrochemistry. So units, joules is equal to moles into coulomb per mole into volt. That means coulomb into volt is equal to joule. So when you do problems, 96,500 coulombs into electrode potential in volt will give you the answer in joules. Okay. So batteries or spontaneous redox reaction. I already told spontaneity is given by delta G condition. Delta G naught is equal to negative. So the delta G sign is negative because the reactions are spontaneous, or another word to tell is the reactions are feasible. Feasibility means possible. Okay. And free energy, delta G is a maximum useful work done, non-expansion work. So this is electrical work here in the electrochemical cell. Okay. So delta G naught, you know all these things we have seen already. Okay. So with this session is over.
Like, share and subscribe. Hit the bell icon for more updates.